The Dust Bowl helped to stimulate serious attention on the fundamental importance of our land. As a result, the basic causes, effects, and remedies of wind erosion have been the focus of research by the USDA's Agricultural Research Service. To understand wind erosion and its control, we need to understand the processes involved. Let's begin with the wind. Wind is simply air in motion. Air has mass, and when mass is in motion, it has energy. It is that energy that moves soil during wind erosion. And it's important to know that erosive wind energy increases by a factor equal to the wind speed cubed, so that a small increase in wind speed results in a large increase in erosive wind energy. The wind high above the soil surface, unrestricted by barriers or objects, is known as free stream airflow and moves more or less parallel to the surface. The wind near the surface impacts the soil and vegetation, which removes energy from the wind and slows it. So the average forward velocity near the soil surface is lower than in the free stream. The velocity increases as the distance above the surface increases. This velocity gradient is known as a wind velocity profile. The nature of the surface over which the wind is traveling can greatly influence this wind profile, as well as the wind energy near the surface. When the soil is rough, large clods or furrows protrude into the wind stream. While these protruding soils are exposed to stronger winds, they also remove energy from the wind and thus protect the lower surrounding soil. This protection allows particles eroding from the upper positions to be trapped in the lower positions. Vegetative material, either live or dead, also absorbs wind energy near the soil surface and can trap moving soil particles. Rough, cloddy, or vegetated surfaces alter the wind speed at the soil surface and reduce the energy available to erode the soil. However, if the free stream wind speed is great enough, the wind at the surface will contain sufficient energy to initiate soil particle movement. There are three phases of particle movement: detachment, transport, and deposition. Detachment occurs when the wind force against soil particles increases enough to overcome the force of gravity. Once detached, moving particles may collide and detach other particles. The detached soil particles are then subject to transport by the wind, either through the air or along the surface. Eventually, the wind velocity decreases and soil particles are deposited. Infield deposition typically occurs in furrows or vegetated areas. Deposition also occurs along the edge of fields, ditches, fence rows, or barriers such as windbreaks. For very fine particles, deposition may not occur until the particles have traveled thousands of miles. The wind speed at which particle movement is initiated is called the threshold velocity and is dependent on the state of the soil surface. A soil surface that is rough or protected with non-erodible material will require a stronger wind to initiate particle movement than a bare, smooth surface. This means that for a given field, there is no single threshold velocity, but rather a range of velocities depending on the soil surface type, aggregation, roughness, crop status, and moisture. Most of these properties can also change during a storm due to the erosive action. There are three ways soil particles are moved by wind: surface creep, saltation, and suspension. Each has its own characteristics and effects. Under surface creep, the force of the wind causes soil particles to roll along the soil surface until the wind slows, they are stopped by other particles, or they are trapped in a sheltered location, such as a furrow or a vegetated area. Surface creep generally involves particles approximately 1/2 to 1 millimeter in size, small enough to be moved by the wind, but too massive to be lifted off the surface. Surface creep contributes to loss and deposition within a localized area. Another mode of transport is saltation, where under the influence of wind, still smaller particles, 1/10 to 1/2 millimeter in size, bounce or hop along the surface. As they bounce, they strike other particles, causing them to move. The higher the grains jump, the more energy they derive from the wind. Because of this wind-derived energy, the impact of saltating grains initiates movement of larger grains and smaller dust particles that can be suspended in the air and carried great distances. Saltating grains collide with clods and cause their breakup, reducing roughness. Saltation also damages young plants, threatening their survival, and can damage their fruit, reducing their marketability. Like particles under surface creep, saltating particles continue to move until the wind slows or they're trapped in sheltered areas. Suspension is where particles less than 1/10 of a millimeter, smaller than the diameter of a human hair, are lifted far above the surface and carried great distances. Some of these form dust clouds that have been traced across continents, oceans, and around the world. Suspension can cause visibility problems. A small fraction of suspension particles may cause health problems when inhaled. These particles are known as PM10, which are particulate matter less than 10 microns in size. The amount of soil that erodes as surface creep, saltation, or suspension depends on the soil type. Soils that are pure sand will move almost completely by surface creep and saltation. However, if the soil is high in clay with clods that break down under saltation, a high percentage of soil loss will be by suspension. On an eroding field, the amount of soil movement will tend to increase with distance downwind due to the impact of saltating grains breaking up clods and initiating other particles to move. If the field is large enough, the creep and saltation flow reaches a maximum that a wind of a particular velocity can sustain. On the other hand, the amount of suspension particles can keep increasing as they diffuse into the atmosphere.